fluids possess energy. This energy is due to variation in the height of a fluid from a reference level and the velocity of flow. There are three types of energy associated with an element of fluid in motion. They are pressure energy, potential energy, and kinetic energy. According to the law of conservation of energy, as the total energy is conserved, the three forms of energy possessed by a liquid are interconvertible. Bernoulli's equation, developed by Swiss physicist Daniel Bernoulli, relates all these three energies. Bernoulli's principle states that for a streamlined flow of an ideal liquid, the total energy per unit mass remains constant at every cross-section throughout the flow. Consider an ideal liquid of density ρ flowing steadily through a tapering pipe from its wide end A to its narrow end B. Let H1 and H2 be the height of ends A and B from ground level. Let P1 be the pressure on the liquid, A1 be the area of cross-section, and V1 be the velocity of the liquid at end A. Let P2 be the pressure on the liquid, A2 be the area of cross-section, and V2 be the velocity of the liquid at end B. According to the equation of continuity, the total mass of the liquid going into the tube through any cross-section should be equal to the total mass coming out of the same tube from any other cross-section at the same time. If m is the mass of the liquid element crossing per second through any section of the tube, then A1V1 is equal to A2V2, which is equal to the volume of the liquid V flowing per second. This can be expressed as the ratio of mass m to density ρ of the liquid. Let this be equation 1. Since the time considered is 1 second, here V1 and V2 are the length of the liquid element of mass m at ends A and B respectively. Thus, A1V1 and A2V2 represent the volume V of the liquid element at ends A and B respectively. Thus, the work done per second on the liquid element against the force due to pressure at A, which is referred to as pressure energy, is given by P1A1 into V1 is equal to P1V. Let this be equation 2. Similarly, the work done per second on the liquid element against the force due to pressure at B is expressed as P2A2 into V2 is equal to P2V. Let this be equation 3. The difference in the work done on the liquid element in moving from A to B is expressed as P1V minus P2V. Let this be equation 4. This difference in the work done is equal to the total change in the mechanical energy of the element. A part of the change in the mechanical energy is used to increase the potential energy of the liquid element and the remainder to increase its kinetic energy. As the liquid element moves from A to B, the velocity of the element increases from V1 to V2 and the height increases from H1 to H2. Thus, the increase in potential energy of the fluid element per second from A to B is expressed as mgh2 minus mgh1. Let this be equation 5. The increase in kinetic energy per second from A to B is expressed as half mv2 square minus half mv1 square. Let this be equation 6. According to the work energy theorem, work done is the sum of the increase in potential energy and the increase in kinetic energy. Substituting and rearranging the terms, we get the equation as shown. Dividing this equation by m, we get equation 8 as shown. As the ratio of mass m to volume V is equal to density ρ, the equation now becomes P1 by ρ plus GH1 plus half V1 square is equal to P2 by ρ plus GH2 plus half V2 square. This relationship holds good at any point in a streamlined flow. Thus, we can say P by ρ plus GH plus half V square is constant across all points in a streamlined flow. Therefore, the total energy of the fluid, which is the sum of the pressure energy per unit mass, potential energy per unit mass, and kinetic energy per unit mass, remains constant or is conserved across all cross-sections in a streamlined flow. This proves that Bernoulli's principle holds good for all ideal liquids in a streamlined flow. We can also represent this equation as P plus ρ GH plus half ρ V square is a constant. Thus, in a streamlined flow of an ideal liquid, the sum of the pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume is always a constant at all cross-sections of the liquid. Bernoulli's principle, however, has some limitations. Bernoulli's principle is applicable only to ideal fluids, that is, irrotational, incompressible, and non-viscous fluids in a streamlined flow. If a fluid is compressible, as is generally the case with gases, volumes do not remain constant, and hence density does not remain constant. Thus, we cannot apply Bernoulli's principle to situations such as this. When the liquid is in motion, the viscous drag of the liquid comes into play, which has not been considered while deriving the expression. When the liquid is in motion, some part of the kinetic energy is converted into heat, but it is assumed that there is no loss of kinetic energy.